Welcome. In this session, we'll explore a method for estimating the minimizer of a function that has a scalar argument where a user has provided us with a fixed step size. Let's recall where we are right now. So the user will give us this data. The user will give us a function and the first derivative of a function. That is, they'll give us a way to calculate these. And the user will give us a first estimate, so this will be the first in a sequence. They'll give us a first estimate of where the minimizer is, and then they'll give us a single value, which is the step size. And our iteration will be, we will estimate the new value to be the current estimate of the minimizer plus a fixed step size in the direction. This direction will be the negative first derivative evaluated at the k point. And here, in previous session, we had a subscript because we were calculating the optimal step size each time. Now we can't do that. So instead, what we have to do is we just have to take that user's best guess at what the step size is. And so let's note that that is where the current direction is the negative of the first derivative evaluated at the current estimate of the minimizer. And so what happens when a user gives us this? Well, we can foresee that if S is too large, we might miss the minimum completely. It may not converge. So it's not necessarily does not converge, but it certainly may not converge. We might get high error. And there may be many other things that could happen. One thing that often happens if the step size is too large is that even if there's a single global minimizer, if the step size is too large, we can see oscillation or hopping as it gradually approaches the minimizer. If the step size is too small, we can foresee that this might converge slowly. So we might have slow convergence, and it might be slow to converge. We might have high error, and so on. Let's now turn to some computer-generated examples where we can visualize what's happening in these conditions. Let's consider this case. Suppose that we have our dynamical system and we're restricting it between 0 and 0.6 as we did previously, and I'll pick a place to start. And suppose we use a fixed step size of 0.4. If we start here and we have a step s of 0.4, then what will happen is at this point in the function, it has a negative derivative with a very large magnitude. And when we multiply this fixed step size times that magnitude, negate it so that we're going in the correct direction, what we end up is here. Now, not only have we completely skipped the minimizer, we've actually made the problem worse, because the value, the level of the function here is greater than the level was where we started. So here we've picked a step size that we think is going to be nice and big and will converge quickly. And in fact, what's happening is we're very close to diverging. If we now take an additional step using this step size, what will happen is now the derivative is is positive, so we have to search in that direction. So let's flip this around. So we're searching in that direction, but now the magnitude of the derivative is very small, and so the resulting step will just be a little wee step here. So we can get some very poor behavior out of a fixed step size if the step size is too large. Now, let's try making the step size small. So let's make it 0.05 instead. And we'll start at the same place, and now I've pre-computed. What will happen is we'll move to here, and then we'll move to here, and we can see that at least we're staying on one side of the minimizer, unlike with a step size that was too large. But this might take a long time to converge. And in fact, our convergence criteria might be such that it terminates before it actually gets us to that minimizer. Now, let's go through some pseudocode. Our pseudocode might start with the user providing us with a maximum number of iterations that we're to take. This is so that we don't have an infinite loop. Part of the convergence criteria might be a magnitude of the derivative. So they may say if the magnitude is less than a certain amount, you can stop. What we'll do is we'll start out by setting our current estimate of the minimizer to be the user's first guess. We'll calculate the function, and we'll calculate the direction that we're going in. We'll start at iteration 0. While we haven't converged, the notes and your code will fill in that convergence criterion. What we'll do is we'll set our new estimate to be the previous estimate plus a step that the user provides us in the calculated direction. We'll update the direction. We'll update the current estimate of the function. We'll keep track of what iteration we're at, and that ends our algorithm. So this is pseudocode for a simple way of computing for estimating the minimizer of a function that has a scalar argument using a fixed step size.